So hi guys, welcome to my YouTube channel. My name is Shank Singh and today I'm going to present you my topic of ATC project. So the table of contents are non-deterministic finite automata. So the first question for today is construct a non-deterministic finite state machine for the language L equals to W belongs to AB, where X and Y belongs to AB and W equals to X A B B B A Y union W equals to X B A B A Y. That means W belongs to either A or B, and Y and X also can be A or B. It can be a string that consists of A's and B's, and this expression uh, tells us that the machine will accept a string which will have A B B A A in it or B A B A in it, because there's a union in between. So if any of these conditions satisfy, the machine will accept the string or the regular expression. So let's construct a machine now. So the first step is here. This is the first step. Step number one, we will create an initial state Q naught. This is the initial state Q naught of the machine. And then step two, we'll create machine in such a way that it accepts the string ABBAA. So that's the first thing that we're gonna do. We'll take the minimum string that will accept ABBA. So we'll require four, five states, which is Q1, Q2, Q3, Q4, and Q5. So for A, B, B, A, and again A. So we'll create first branch that will accept ABBAA, and Q5 will act as the final state for this branch in order to accept the string. So if we move forward, here this branch has been created, and if a string that contains ABBAA comes into the as output, this branch will come into action and it will accept it. It can reach the final state. Now because we had union in between, so we'll have another branch that will be used for accepting this string BABA. So this branch here will create four more nodes named Q6, Q7, Q8, and Q9, and then they will be used for accepting this string. So let's see how it works. So yeah, here this will be the final machine. This is something our final machine will look like. One branch will be there that will accept A, B, B, A, and Q5 will be a final state. And then there will be another branch which will accept B, A, B, A, and it will accept B, A, B, A, and Q9 will act as a final state. So in this diagram, we have one initial state and two final states. So this will be the final structure of our Ndfsm. Now let's move on to tracing part. So here I have some screenshots of the tracing that I have done using JFlap, but I'm going to show you live. So let's log on to the finite automation section, and I have already created a file over here that I'm going to show you. Yeah, so this is the file. This was the machine that I just show you in the docs format. Now let's take some input. So we wanted that a string should contain either ABBA or BABA. So let's take an input like AA, ABB, AA. Okay. So step one, two. So it is not going to be accepted because this strings doesn't lie in the range of the accepted string. So it will give a wrong answer. Now, again, if we do it for a string A, B, B, A, 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 B, B, A. Okay. So if now we do it, step 1, 2, 3, 4, 5, 6, 7, 8, 9, and green. This green symbol shows that our string has been accepted because because A, B, B, A, A comes in the string. So it will get accepted. Again, if I show you for some another input, let's take an input like we also can accept BA, BA. So let's take an input like B, A, B, A, 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 B, B, A. These are just random inputs, they don't mean anything. So start 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, there was a green signal over there, which means that this string would be accepted because it had BABA in its as a substring, so it will be accepted. Now let's move to the second part of our presentation, which is the Turing machine. This was all about the finite Ndfsm, which is non-deterministic finite state machine that can take multiple outputs as a for a particular input or for a particular space. So now we can start with Turing machine. So Turing machines are used for checking whether a string will be accepted or not. They decide whether we need to go right or left for every step or every state. We can have two transitions, either left or right, and that will decide the forte of our string. So as of now, we have a question, which is construct a Turing machine to set accept the set of all strings containing the substring at 1001, where w belongs to 0, 1. So basically we have been given an input string that should contain 1001, and if it contains 1001 it will be accepted, otherwise it will be rejected. So let's create a Turing machine for it. First step, step number 1, we'll create an initial state q naught, and it will not be the final state because till now we haven't got a string which is 1001. Now the step 2, our Turing machine will look something like this. Yeah, a Turing machine will look something like this, where if we enter 0 in the first place, it will replace it with x and move to right, because till now there's a scope for 1001 to be found in further in the string. It will move to right, and if it founds 1 in the first position only, it will replace it with x as well, and will move to right, because this will be accepted in 1001. Now if it gets accept if 0 comes, it also gets replaced with x and moves to right. Again 0 moves to right, then again if 1 comes, it will be replaced with 1 and will move to right, and will get q4 as a final state. So the simplest thing that we can check is 1001. So if 1001 comes, we will reach to a final state which is q4 from the initial state q naught. Now we can talk about some intermediate stages. So suppose if I receive q a 1 at q1, like something like 11001, so it is also a valid string, and 1 will move it, and it will move to right at this place, and it will remain to the same state q naught. If we receive 1, it will receive to the same state q naught until the time we keeps on repeating 1 1 1 1 1, it will stay at this particular state q naught, sorry q1. Only when it receives 0 as the next character, it will move to another state q2. Now, another intermediate state could be where at q2 we receive a character 1. So it's something like 101. So it will not be a valid string, but still we have a scope for the string to be found further. So we'll send it back to a state q1, and it will move to right. So 1 will be replaced by x and it will move to state q1. Now if suppose we have 101 001, so 100, it will move to this place 0. And here also, if was now 1 comes, then we will reach to a final state. But if 0 comes, then we'll again go to state q1. So only when we receive 1001, at that point only we can claim that we have reached the final state q4, and our string has been accepted by the Turing machine that we have created. Otherwise they will move to some other stages and it will create some intermediate transitions, and it will move till the time we don't get 1001 and our tape has reached the blank. So this was about our construction of the Turing machine. Now let's talk about its implementation. So for implementation, we'll again move to JFlap. So we'll again move to JFlap. Just a minute. Yeah. So this is the JFlap file that we have created in advance. Just a minute. Okay. Yeah. So when we take input string as 01011, so it obviously won't be would be rejected because accepted string was 1001, and this given string does not contains the required string, so it would be accepted, it would be rejected. So that's what it does. When we take 01011 as our answer as an input string, we get red screen, that means it had been rejected by our machine. Now let's take some another input, which is 1001. If we take 1001, it's obviously the smallest input that we could think of, and it would be accepted by the Turing machines. That's why the color of the screen here shows green. So it will be accepted by the machine, and the process will terminate. So these were the two topics that we were assigned for today's presentation. This was all for today. We'll meet next time. Till then, keep studying. Thank you very much.